Okay,
It's really
so
bright in here today, I feel like.
let me give you some hints on, and again, this whole overall process. So there's the rate law, and then today we'll get into what's called the integrated rate law. So there is no other process when you have a set of data like this. So the whole idea being is that you are manipulating the concentrations of reactants in the reaction. And you're basically saying, hey, what does that do to the rate? So physically, the hard part of this is that how do you measure the rate? How do you measure the change in the concentration of something? So like the lab that you all are going to do on Monday and Tuesday, we're going to pick iodine because iodine has a distinctive color. So you can say, oh, okay, hey, when the iodine is present, it has a certain color. And as that iodine gets used up, the reaction fades out, and once it goes clear, oh, that's when it stops. So that's something that you can measure. You can measure hydronium ions. Oh, you can measure pH. How does pH change as a function of time? So when you get to the purple sheet, I emphasize this is a process, okay? So what you want to show me is that this just has two of them, A and B. So you want to choose reactions where you can cancel things out, and it's just comparisons of rates. So what you should see is that this is first, on that first one with A plus 2B yielding 2C, you should see that both of those are first order with respect to A and with respect to B. Okay? So what that means is if you double a concentration, you're going to double the rate. Now, here's where this, you can't just look at the equation. So if you look at A plus 2B yielding 2C, and if all you saw was that, you would think, oh, this should be dependent upon the concentration of B squared, because there's a 2 in front of it, okay? But, and if it was just a simple, and we'll get into this later, what's called a mono-step problem or a simple one-step reaction, that would work. But when we actually look at the data, we change the concentrations, we realize, hey, that isn't how that works. So the whole point of this being is that you can't just look at the coefficients and go, oh, that's going to get squared, that's going to get cubed, whatever that is, okay? That's the whole point of this. All right, so your K value should be a horrible GPA. I mean, a horrible GPA. And on C, when you're trying to figure out what the initial rate of the disappearance of A is going to be, that should be something, it should start with a 4, and it should be times 10 to the negative 4th. Okay? When you get to that second one where you're forming Nober, it's kind of fun to say, that K value is going to be really big, and it should be something times 10 to the 4th. Now, make sure that you have K values, when your K values, make sure they have units on them. If you just say, oh, my K is 1.2, cool, no, okay? If it's a lowercase k, and it's that rate constant, you have to have the units with it, okay? You have to have the units. Uppercase K, no units. Lowercase k, got to have the units, okay? Cool with that. Okay. On the photocopied page, the rate for that phosphorus, or that P4, that should be something times 10 to the negative 4th. And for the hydrogen, that should be something times 10 to the negative 3rd. And again, you could either set that up algebraically, where you go, oh, 1 over 4 times the change in rate of your pH3 concentration over time equals, times the change in the concentration of your P4 over time, plus equals 1 over 6 times the concentration change in H2. So you could do it that way, Okay, that's an option. Or you could just do the stoic. Okay, I don't care. You're going to get the same answer either way. It's whichever one that you want to do. Makes me no difference. When you get to 23, you should see that it's second order with respect to one of them and first order with respect to the other one. And your K value, and this is in minutes, okay? And you can leave it in minutes, that's cool. If you left it in minutes, that K value should be around 180.
What if we switch seconds?
Huh?
What if we switch to seconds? What should it be?
I don't know. I don't have it. I just got it in minutes. So I don't multiply by 60 and there you go. On 24, you should see that that's first order with respect to both of those. And on 27, your K value, and this is in micromoles per second, because that's what the units are that they have. So on 27, your K value should be around 0.3. Okay? Anything else on that one? Going once, going twice. So stop that, get that.
Like, what if I just took my car and left?
Just ran away.
That'd be kind of funny.
Yeah.
I think people would notice.
Could you afford enough gas to get out of the state?
Yes, I could, actually.
Okay.
I know.
All right. So here's the next step in our journey.
In our journey?
In our journey. So what we did yesterday was the rate law. So if you need out this sheet of lecture notes, okay? You gotta have this because this is gonna make life so much
Do you
so
have
much
a spare,
simpler.
Mr. Bridget?
Huh?
Do you have a spare?
It's on the back of your left. Oh.
I don't know where mine ended up.
I was talking about a spare tire for a second.
There's a possibility, but I don't think it's a very high possibility.
Huh.
Thank you.
Let me do it.
I'm writing my name on this.
Wait, Bert, how'd the little interview thing go?
I went well. It went well. Did the first two out of the array, and then came in here and did demos with static electricity and.
Yeah, I saw you on someone's story.
Okay.
Tyler's. Yes, Tyler. I was
Okay.
like, wow. So I thought you said you didn't want a audience.
Well, I brought him out there and I
It's
told
not
him this
us,
is
I
like
guess.
my,
Yeah, literally
my
what?
therapy support class. So, anyway. All right. So, what you all did yesterday was called the rate law. And it works, but the disadvantage of it is that you don't have any values of time. So, the integrated rate law, which oddly enough, if you take the integration of the rate laws, this is how you do this. The advantage of all of these is that they involve time. Now, here's what's going to be most important. So on that sheet that I've given you, you have three different types: zero order, first order, and second order. Okay? The first and second orders are by far and away the ones that will be most common. It's rare that you see a zero order reaction. Okay? It happens, but it's very, very rare. Most of them are first order or second order. So, let me kind of lay out the difference. What's common to all three of these is that in a weird way, if you express it like I have, these are all linear functions of y equals mx plus b. Okay? Now, if you look at these, you go, that does nothing at all look like a linear function. Okay? You've got like natural logs, you've got inverses, no. Okay? Trust me. Trust me it is. So, let me kind of lay out the format for all of these. So, they're all in the form of a linear function, y equals mx plus b. So what that means is that if it's zero order, you would graph the concentration of A on the y-axis. Then all of these involve A naught. A naught is the initial concentration of the substance at time 0. Okay, the other thing that you'll see is that all of these involve time. So that's going to be my initial concentration. And it's always going to be a concentration of a reactant. So at A naught is as high as the concentration is ever going to be. It's always going to decrease from there. So it's always going to be based upon the initial concentration of one of the reactants. Also, they all involve some value of K times time. And that lowercase k is a rate constant, and it's going to change depending upon the reaction. So, whatever you have over here, 1 over A, natural log of AA, whatever that is, that's what's going to get graphed on the y-axis. What's going to graft on the x-axis is going to be time, okay? So that's going to be cool. So time is always going to go on the x-axis. Usually it's in seconds, could be in hours, most of the time it's going to be in seconds. Then this is going to be your y-intercept. So on this one, your initial concentration, if it's 0 order, your initial concentration is going to be that. If it's first order, the natural log of A naught will be your y-intercept. If it's second order, 1 over A naught is going to be your y-intercept. So they all have the exact same format of y equals mx plus v. Now, this is where it gets tricky in terms of the units of k. So let's start with 0 order, because you need to understand the process and just not, oh, magic happens and this is what this is where it works. So if you look at 0 order, okay, and you have A equaling negative KT plus A naught. Now, units are vital, absolutely vital. Since these are just concentrations, this is just going to be molarity. Okay, that's it. It's molarity. This is going to be molarity over here. Now, here's the deal with units. You can only add like units. Okay, I can't take molarity and add that to liters. Okay, I can't take molarity and add that to seconds. So since this is going to be a linear function, everything has to be the same thing of molarity. Okay, that's it. So what that means is that this time is going to be in seconds. So somehow I have to get rid of the seconds and end up with this being molarity. Okay? So I'm like, oh, right, what can I multiply that by? Oh, right. Maybe molarity per second. So if you look at this, okay, that's why down at the bottom I said, hey, here are the units for K. The reason that that's molarity per second for K is that when I take molarity per second times seconds, the seconds cancel out. Now I have everything in terms of molarity. Now, here's the other reason why it's molarity per second. Because you're going to draw a graph, and you're going to have the concentration of A on the y-axis, and you're going to have time on the x-axis. Ah, cool, right. Slope, here we go. It's going to be some linear function like this. So what's going to happen is that you're going to have some initial concentration of A. It's going to be high concentration. It's going to get consumed, and the concentration is going to decrease as a function of time. So what that negative sign indicates is that this is going to be a negative slope, okay? Don't look at that negative and go, oh, I'm going to take a negative of a negative and it's going to be positive. No, the only reason I put that negative sign in there was that when you look at this, you go, oh, this should be a negative slope because the concentration is decreasing. So here's the other way that you know that it has those units. Because if you look at change in y over change in x, oh, that's kind of cool. My y-axis is molarity. My x-axis is time. I get molarity per second. So there's two ways that you should understand how you get the units for K. Number one, the units have to work out so you can add everything together because it's a linear function of y equals mx plus b. The other thing is you look at the graph, okay? So that's 0 order. Rare that we're going to deal with anything 0 order. Vast majority of what we're going to deal with is going to be first order and second order. Now, if you look at what's on your equation sheet, you have the general form of these equations, but they do not tell you which is first order and which is second order, okay? That's something you have to know. This is how I remember it. This is natural log. Oh, that looks like a 1. The L looks like a 1. That's how I remember that natural log is first order because it has an L in front of it, and that looks like a 1, okay? That's just how I remember it. If you want to use that, great. I don't have it, copyrighted or anything. You can use that, okay? Or you can come up with your own. I don't care. Now, here's the important part of natural logs. Okay, so you have the natural log of A, okay, and I'm going to rewrite this. It's going to equal negative KT plus the natural log of A naught. Now, here's the deal. This is hugely important in terms of units. And this only happens with natural logs. Once you take the natural log of something, all the units disappear. Okay? So as soon as you take the natural log of anything, there are no units left over. It's gone. Out. See ya. Okay? No units. So what's going to happen is that over here on this y-axis, you're going to plot the natural log of A, which means that that has no units. Okay? There's no units. Nothing there. It's not there. No units. But I've still got time here. So then when I look at the slope of this, oh, that's change in y over change in x. So I have no units on top. The only thing I have are seconds in terms of units, which are down below. So this becomes 1 over seconds. Because as soon as I take the natural log, the units disappear. It's the only time you'll ever hear me say this. Natural log, boom, units are gone. So these graphs are going to slope down like this. This is why there's a negative sign in front of that, because that's going to have a negative slope. Okay? So this has no units. The natural log of A naught has no units. Time is going to be in seconds, so the only way that I can make this work out is if my K value has 1 over seconds. Okay? So 1 over seconds. So this is why this works, because of the fact that my KT value can't have any units, because when I take the natural log of stuff, that doesn't have any units either. So you can look at it in terms of slope. You can look at it in terms of units. Okay? Whatever works for you. Now, second order. On second order, this is one that's an inverse. So you have 1 over the concentration of A equaling KT plus 1 over the concentration of A naught. Okay? So, oddly enough, you're going to take the inverse of molarity. So EMA, if I take the inverse of molarity, what do I get? No, do not make this difficult. Do not make this difficult. I'm taking 1 over molarity. What units do I get?
Into the negative 1.
Yeah, m to the negative 1 or 1 over n. That's why I said, do not make this difficult. Do not make this difficult. Okay? So this is going to be m to the negative 1, or you could leave it as just 1 over molarity. I don't care. Pick one. So oddly enough, this also has to be 1 over molarity. Okay, well that's cool, right? So here's my KT value. Oh, right. When I multiply K and T together, what do I have to get? EMA. What do I have to get when I multiply K and T?
You have to get molarity by itself, so you would do, yeah? Oh, you have to put molarity on the top.
On the top. Does it help if you get lyrical and sing like that?
You have to have, yeah. I don't know.
Okay, I've never had a student answer in lyrical singing like that. I feel like a monk. Okay, so I got my KT value. So I'm going to, because my time is going to be in seconds, right? So I've got to get rid of my seconds. So I know I have to have seconds down below to get those gone. And then I could just put molarity here. So if I multiply seconds by 1 over molarity seconds, I get m to the negative 1. So there you go. Now, again, look at the slope. Oh, on this axis, I'm graphing 1 over molarity. On my x-axis, I have time in seconds. Oh, cool. When I do change in y over change in x, I'm taking 1 over molarity divided by seconds, which is also 1 over molarity seconds. And if you don't like that, you can put m to the negative 1, s to the negative 1 if you really want to get fancy, okay? Use your negative exponents. Okay, got the idea. Okay. Now, on the sheet, which I don't have because I lent it to someone who lost theirs,
I think Zach's
down at the bottom,
mine, bro.
you have a formula for half-life. Tomorrow I will go through and show you where that comes from. I don't have time to do it right now. But here's what half-life represents. Half-life represents the amount of time it takes for the concentration to decrease by a half, hence the term half-life. So let's say that the half-life is, I don't know, 30 minutes. Okay, you know the half-life of a reaction is 30 minutes. So if the initial concentration is 0.50, 30 minutes later, that concentration is going to become 0.25. 30 minutes later, it's going to be 0.125. It's going to keep going by halves, by halves, by halves. Evan?
But I thought earlier when you were showing us the graphs, the concentrations decreased at a linear rate.
Here's the deal. So when you look at your half-lives, half-life concentrations change depending upon, some of them are dependent upon initial concentrations and some of them aren't. Okay? We'll get into that. Hold that thought for tomorrow. Okay? So what you need to know for today on the half-life values, the half-life is determining how long it takes for the initial concentration to drop to half of what it was initially. Okay? Because some of these are dependent upon initial concentrations and some of them aren't. We'll get into that tomorrow. Okay, so hold that thought. Okay, so here's how these problems play out. So what you're going to have is, nope, not what I want.
Can you go through your portraits over the years?
No.
Where are these socks?
Selfie.
For one night, embrace yourself.
Huh?
You should buy the socks and tell us what happens, babe.
No. Okay. Now, here's the one thing I will promise you. I will never do this. I'm never going to show you this big, long process. And then tomorrow you're going to walk in and I'm going to go, oh, you don't have to do all that. You can just do it in one step. Okay? I will never do that. I promise you. I will always show you the best and most efficient way to do any problem right from the get-go. So, here's how this is going to play out. You have some reaction. Hold on, I didn't export this. I always forget that I've got to export this.
Pretty team.
No.
Did you use this equation? Verb?
Yeah, I think
How's your TV
that's
there,
what I
Bert?
did.
What do you mean?
There's like spots on the screen.
It's my fingerprints from going like this.
That makes sense.
Yeah. Okay. So here's what you're given. On a problem like this, you're going to be given a data table of time and concentrations. Okay? That's what you have. The very first thing that you have to do, is that you've got to go in and you have to take the natural log of these concentrations. Okay, that is the first thing that you have to do. Okay, that's it. The second thing you have to do is generate another column of the inverses of A. That's it. First thing you have to do. Okay, there's no shortcut. You have to do that. First thing. So I did this. Okay, so all I did was I literally punched it into my calculator. Natural log of 0.01, natural log of 0.7, okay? And I generated this. When you do this, don't round these numbers too much, Okay? Now, you don't have to have 10 decimal places, all right? But don't look at this and call that, oh, I'll call this -5 and -5 and no, okay? You have to have some decimal places out there. I'm not saying you have to have 20 decimal places, but you just can't round it to like a whole number. Same thing is going to be true of these inverses. Okay, so that's what you've got. So the first thing you have to do is generate those columns. Now, here's the second thing that you have to do. So you've got to decide which one of these two sets of data is linear. Okay, there's no other way around it. So what you have to do at that point is that you've got to go through and you have to draw a graph. So if you look at the graph, oh, I thought I included that graph.
Isn't it an attachment on that side?
Oh, it is. There's the graph.
Did you email yourself?
Yeah.
I do it all the time. I also do that.
Wait, like how recently?
Do that, Joe?
What do you mean?
Like,
You said that and immediately got ganged up.
never mind.
Email himself with his. Yeah. Yeah. You don't do that? Yeah.
Potato,
Yeah.
potato.
Just a person.
You can do it with
What is it?
Well, yeah.
That's what we did mine.
Years.
Yeah, you can text yourself. That's
Yeah, I
text
text
yourself.
myself.
Okay.
I've done that before.
Now,
Sorry.
That's sad, actually.
what? Text yourself?
Yeah.
I don't know.
Doing a program.
I do that when I need to remember important information.
Yes. Okay. So I'm going to show you two different techniques depending upon how comfortable you are with graphing. So what I do to kind of save myself some time,
That makes me uncomfortable.
I come along here and I put my time on that x-axis because that's always going to be true. Time is always going to go on the x-axis. 0, 100, 200, 300. So over here, what I did is that I did this so I could put both graphs or both sets of data on the same graph. So what I did is I came over here and I put natural log on this y-axis, and then I put my values of inverse of mass over on this axis. Now, if that's going to flip you out, and you go, well, can't handle it, nope, nothing to do, okay? If that will flip you out, just draw them as two separate graphs, okay? Huh?
I feel like Gracie wouldn't like that.
Okay.
I'm
Some people like it. It flips other people out. If you look at this and go, oh my God, sensory overload, can't do it, then don't, okay? Draw them as two separate
my
graphs.
brain.
I did it this way just so that I could look and go, oh, this is what I've got. So what you should see is that one of them, when you graph them, one of them should be very linear, and the other one, oddly enough, is going to be nonlinear. Okay, Evan?
Do we have to graph them both if we get lucky on the first try?
No, you are initially you're going to graph them both. Okay, that's the deal. Okay. Now, the other thing that's probably going to happen is that it's not going to be exactly linear. So what I did is that when I drew these points, I came through here and I picked a couple of points to find my line of best fit. Okay, so that's what I got off of here. So then I came down here and said, okay, now that I know when I looked at this, the graph of 1 over A was the one that was more linear, okay? The natural log was curved. So that's how I knew, oh, that's the one that I'm going to pick to find the slope on because that was the one that was most linear. So all I did here was I went through and I found the slope. Here were my data points that I picked. Okay, boom, boom, got my time, found this, here's my slope. Now, once I get the slope, and that's the hardest part, once you get the slope, everything else is gravy, okay? So once you get that slope, then you can come down here and say, okay, I know this is a second order reaction, so that means that I've got 1 over A is going to equal my slope, which in this case is going to be 0.55, 1 over molarity seconds. times time plus 1 over A naught. Okay? Now, this is where, like, the magic happens. Once you get this, now you can do a whole bunch of different things. Now I can find my half-life once I have that value of K. If I want to find the concentration and say, hey, what's the concentration after 150 seconds? Oh, right. I can plug in 150 seconds. My initial concentration is never going to change. That's a fixed value. So if you go back to this, so my initial concentration, that's my A naught value. That's 0.01, which is going to be, when I take the inverse of that, that's going to be 100. Okay? So now, what I could do is, now that I have that information, I could also write this as 1 over A equals 0.55, 1 over MT plus 100, 1 over molarity. Okay? I could do it that way. So if you actually want to have that, what that y-intercept is, once you take the inverse of it, boom, there you go. So you can do a whole bunch of different things with this. So now that you know that it's the integrated rate law, you can also write the rate law itself. Oh, this is second order. So I could write that as R equals K. Now I know what K is, which is 0.55, 1 over molarity seconds, times that A squared. Now, this is also where the magic happens. Oh, this is actually going to be my rate. Cool. So, if you look at this, what's any rate measured in? Molarity per second. Always molarity per second. So now, if you look at this, this is where these two ideas merge together. So now I've got this. Oh, that's molarity squared. Okay, because it's the rate law. That's molarity squared. I multiply that by 1 over molarity seconds. Those cancel out. I get molarity per second. It still works out. Okay, so once you view this holistically, you say, this is how all these pieces of the puzzle fit together. So the rate law and the integrated rate law fit together because they're both going to have the same value of K with the same units. There you go. Like I said, if there was a shortcut to this process, I would tell you. But there's not. So you literally have to draw the graphs, generate the data, draw the graphs, see which one is linear. So stop that for a second. Okay. So there's a total, this is why I said there's only 4 problems. Okay? There's only 4 problems. Only 4.
So funny.
So, here's what I've got up here at the beginning. Some gas A decomposes into another gas B. That's it. So, I've given you the molarity of A as a function of time. Time 0, it's 0.01. So notice as time goes by, your concentrations are becoming smaller and smaller and smaller because A is turning into B. Okay? So the first thing that you need to do is take the natural log of those values and then take the inverse of those values. That's it. Then you're going to graph that. Okay? So I'm going to give you all graph paper. And again, you can do this one of 2 ways. If you want to put time on the x-axis and you want to put natural log over here and you want to put 1 over A over here and combine them onto one graph, cool. Okay? If that's going to flip you out, do them as 2 completely separate graphs. Okay? It is totally up to you. But you need to listen to me. With a ruler, you need to draw a line of best fit. Okay? And you need to pick points that are actually on the line. Okay? That's the whole point of this. Okay? Because these aren't going to be exactly linear. Okay? You're going to have to say, okay, hey, what's going to be that line of best fit? Now, so you're gonna, when you get down to like number 4 where I said write the general equation for the line, that's y equals mx plus b. If it's first order, you're gonna start off and go, hey, natural log of a equals the slope times time times the natural log of a naught. If it, and by the way, these are all going to be first or second order. Okay, there will not be any zero order. All of these are going to be first or second order. Let me give you a hint. There's a total of 4. 2 of them are first order, 2 of them are second order. Okay? Now, on we get to number 5, let me give you a hint. You want to know, hey, what's the concentration of A after 100 seconds? Look at your data. At 80 seconds, the concentration is 0.045. At 120 seconds, it's 0.03. So at 100 seconds, your concentration has to be somewhere between 0.045 and 0.03. This is it. Okay? It has to be somewhere between those two. Now, let's just say hypothetically it's a first order reaction. Let's just say. So I want to make sure everybody's cool with the math. You have the natural log of A, and I'm just going to make up a number, and let's say the K is negative 0.10, 1 over seconds, and then you're going to have 100 seconds, and let's say the natural log of A naught is 0.5. I'm just making up the numbers, okay? Literally, I just completely made up these numbers. So what you want to figure out is the concentration of A after 100 seconds. Mathematically, how are you going to get A by itself? How do you undo a natural log? E, okay? So you should have an E function on your calculator, okay? So you're going to get all of this, and then you're going to take E to that value. That's how you're going to get A by itself, okay? If it's second order, it's just going to be the inverse, and you flip it over. So here's the beauty of this. When you get your answer to number 5, and you want that concentration after 100 seconds, come up here and see if it's somewhere between 0.045 and 0.03. If it is, odds are you did it right. If your concentration at 100 seconds isn't between the 2 data points, you've done something wrong, okay? So that's where you can just look at your data and go, hey, does this make sense? Now, the formula for the half-life and the numeric value. On that sheet that you all have with that big grid, it's like chemistry bingo, I have formulas for the half-lives down below. Now, look at this. Your initial concentration is 0.1. By definition of a half-life, the half-life is going to be how long it's going to take for that concentration to become half of 0.1. Well, half of 0.1 is what? 0.05. So if you look at your data, okay, at 40 seconds, the concentration is 0.067. At 80 seconds, the concentration is 0.045. So when you look at your data sets, you go, oh, great. My half-life has to be somewhere between 40 and 80 seconds, because that's when that concentration is going to drop to 0.05. So use your data to see if your answers make sense, okay? On the back side, only do 29 and 31, okay? It's all the only ones that you have to do, 29 and 31. Now, what you want to be careful of is that on your times, notice that they changed the values of the times. When you look at like 29, the first time was 120-second intervals. Then the next one, they're going to 300. Oh, that was a 180-second time difference. Oh, and then you're going to 600. Oh, that's a 300-second time. So don't get trapped in this idea that the times or the changes in time are always the same. You have to watch those time scales to make sure that you're actually plotting what those points are. Okay, I'm done. Good luck. You're on your own.